So in today's tutorial, we will be focusing on the implementation of an input-output class that is able to handle pure raw data. That means data that has no meta information about its contents at all. And yeah, we will investigate how we can approach that and potentially some minor aspects that we need to pay attention to when working with this I/O later on, because there is yeah, some minor points that are different from I/Os that actually have access to meta information, but we will come to that. First of all, I set up everything pretty much the same as we were used to in the last tutorials. The only exception is that this time we don't need the OpenCL module because we're not creating any projections and not working with some kind of image filters on the GPU. So only the CTL core module and the QGUI module, and this is only included so that we are able to inspect the data that we loaded. But this is also optional when it just comes down to implementing the I/O itself. And the other things I set up is I've prepared some test functions that we will use later on to verify that we can actually write and load data in the correct fashion, and some example that we will go through in a second. And apart from that, I just created a file rawdata.io, rawdata.io.h, where we will put the code for our raw data reader and writer. And one difference with respect to the previous tutorials is that I will not be using namespace CTL from now on, and the reason for that is that there is quite a high likelihood that some of the implementations that we will go through in these tutorials will make its way into the CTL library, and I want to avoid that we have naming conflicts when we're using namespace CTL and then the class has the same name as it has now in our tutorial, and if people later on with a newer version of the CTL will try to run the tutorial, they get into issues with identical class names. So that's why I will be using the CTL namespace, or I will be writing it now explicitly all the time in the tutorials. Okay, so then we can quickly take a look at this example that I've already prepared, and this is just very simple, basic example going through how we normally deal with our I/Os. And in that case, I took the NRD file I/O, and I have two files on my disk that I have placed in this data folder here, and these two files that we take a look now they are scandata.nrd and volume.nrd, containing projection data and volume data. And as you probably all know, we just create our BaseTypeIO reader and passed it as a template argument the type of file that we want to read, or let's say the corresponding I/O for that file type, in that case the NRD file I/O. And then we can just straight away read projections from that file and visualize them. The same goes for volume data, and we can also read single slices from that volume, visualize that, and then later on we will take a look into this example here, how we can test writing and reading in a consecutive order. This is just to illustrate how we normally work with these files, and we can quickly run that example to see how that looks like. So we have these three visualizations here. So the first thing is our projection viewer that read the projections from the NRD file. We can see the dimensions of the file if we would like to, and can go through the data. Then we have our volume viewer showing the entire volume that has been read from the file, which is a simple ball, if you can probably see here in this example. And then we just read slice 20 from that full volume file, visualized here in this chunk 2D viewer, just the slide at position 20 from that file. And for testing how to write and read the data, I create some dummy objects so that I really know what is in there. I've created a projection data object with some arbitrary dimensions. I allocate memory for 7 views and fill it with the extinction value of 8, and I create a simple cube volume object, and then I pass these into my test save load function, and we come back to what this means in particular a bit later on. So let's for a second just take a look into these functions. They are very simple. We just start out with writing the data that we pass into a temporary file, then reloading the data, and then just computing the RMSE between the data that I passed in and the data that I loaded from the file that I've just written. So this is a very quick and simple method to more or less verify that we can write everything that is in the data, and after we read in the data again, that everything is restored to their original contents. This is by no means a complete test of the entire I/O, so it's just testing this one particular individual aspect, but it gives us a first indication of whether or not we have done everything appropriately or not. And the same goes also here for this second function, where I just want to load one individual view. So that's very similar to what we've seen in the visualization example. For one slice of a volume, we can also read one single projection from an entire set of projections. I also compute the difference, and the same goes for a volume data set. And there would be way more things to test, but these three should be sufficient for us now to get a first impression of how things are going. And now the thing that we want to do is we want to basically replicate this exact same example here, but with a file I/O that can read raw data without any header information. So the first thing that I will do is I will just copy and paste that code into my second example function, which we will now also be executing. And what we want to have is we want something here that is no longer an NRD file I/O, but something, I will call that a raw data I/O. And we will see that we need to do some modifications. Just a pure class will not be enough for us, but we will see that in a second. And then we want to try to read data from the same files, but with the ending .bin to indicate this is binary data, just in raw data format. So they are also in my data folder, and all the data that I'm using here will be provided in the repository for the tutorial code as well. Okay, so when we want to implement our raw data I/O, I already said I created a file already for that, but the first thing I recommend doing is taking a look into the documentation, and in particular now we want to take a look into the BaseTypeIO class, because this is where we can find information about how we actually can implement this file I/O implementer that we now need to do, that we now need to provide to be able to read raw data files. And probably you remember that in the very first of these advanced tutorials, I mentioned that this is one of the cases where we have a little bit different approach, where we do not inherit from an abstract base class and just override some virtual methods, but we have a little bit different approach here for the file I/O. And if we go through the documentation, we can find this section here, which describes what a file I/O implementer needs to provide in order to be functional, to be used inside this BaseTypeIO, which then allows us to very easily just read projection data, volume files, and so on in the correct CTL format. And there's also a lot of information here on what these particular methods really need to do. Since I know that already, we can skip that for now, and I will tell you about these when we implement the methods. So for now, we just copy all these methods because these are the ones we need to provide for our file I/O, and then can start right away by implementing the class. So this will be our class raw data I/O, and we need to provide all these functions here, and we need to first of all start with including all the headers that we need. And the first thing we need is qvariant map, which then in turn will already include few other Qt classes, so that's why we don't need to include qstring explicitly here. And then there will be some further things coming up, but we will come to that when we arrive at that position in the code. So I already mentioned before that just having this class as it is will not be sufficient for us. And the reason for that is that since we have no meta information in our files, there's no way for us to know the dimensions of something we read in. And that's why this is something we need to provide to the class. We need to pass that information in, how the dimensions of our raw data is supposed to look like. Maybe some of you have used raw data import in ImageJ, for example, and as you might recall, then you need to specify at least the first two dimensions, and then ImageJ is able to read the data into the correct format. And something pretty similar we want to do here, but for sake of simplicity, we will specify all three dimensions, and we also need to specify the type of the data that we read in. That's also the same when you read raw data with ImageJ. And if you again take a look at how these implementers are used within the CTL, you see that you need to pass them in as a template argument to our BaseTypeIO, and that means all the information about the size of the files that this IO can read needs also to be known at compile time. And that's why the solution that we can come up here with is to make this class a template that takes the dimensionality of our file as an input. And that's exactly what we want to do here. So we create this class as a templated class, and it takes our three dimensions of the file as unsigned integers here. We will discuss briefly if we really need the third dimension in the very end of this tutorial, but for now we will keep it here. And then we will also give it some type name, which I will call the raw type. This is the type our individual data points or individual values in the file will have later on. So this could be float, integers, short, whatever we pass in there. Okay, and then we can directly proceed with implementing all these methods. And I want to start with this meta info method because it's basically the simplest one in our situation here. And we can leave that in line here. And we can try to take a look how that needs to look like. So in general, this meta information or meta info method is supposed to extract all the meta information from the file that is passed in here and then put that into a covariant map that has some specific demands, which are explained to quite some degree in the documentation. So you can read that if you want. And in our case here, there is no meta information in the file. So that's why we actually don't need that file at all, because we don't get any meta information from that. And the meta information that needs to be provided through that method has a minimum requirement, and the minimum requirement is that it needs to specify the dimensions of the object. So number of whatever pixels in X, Y, and Z direction, for example. And this is something we have because we specify that as a template argument of our class. And therefore we can implement the meta info method without having access to meta information in the file. And what we're going to do is we will create a covariant map that we want to return in the end. And then we need to insert the correct tag for that. And if you take a look in the documentation, you will find that, but I will provide that here for you. We need this from the IO namespace in the CTL. We have some meta info tags, and for them to be available, I need to include them first. So we include the meta info keys header, and then we can find that there are a few number of tags available. And in this situation, I want I want to have the dimensions object that I need to create, which provides a few number of constructors. We need the one with 3 dimensions, and we just simply pass in our 3 dimensions here. And then all we need to do is we need to insert this dimension object into our covariant map that contains all the meta information, usually from the file, but in this situation from our, let's say, prior knowledge about how dimensions are in this situation. And this needs to go under a certain key in the covariant map, which can simply be extracted from this meta information that is provided in this file. So this will give you the correct key that later on the CTL knows where to look for these dimensions. And then maybe this code looks a little bit strange to you, but it's basically just taking the information from that dimensions object and putting that to qvariant. So you can think about of that as some kind of explicit conversion from my dimensions object into a qvariant, because you probably remember from all our examples of serialization that in this qvariant map we always map a qvariant to some particular key in the map. And then we're already done, so we can now return this this qvariant map, and we've provided all the meta information that is actually fully required. So this would be all that is needed in any kind of file IO implementation. But of course, in case you have an implementation for a file type where you have lots of meta information, it is a good idea to extract as many of this information from the file and put that in this qvariant map, because then later on, probably remember the example where we looked at meta information reading from files, then you have the chance to extract everything from that meta info object later on, what was in the file. Yeah, because everything that you don't read out from the file and put in this meta info map will not be present for the user later on to be able to work with. So that's usually how it's supposed to work. Since we don't have meta information in actual pure raw data files, the only thing we can do here is place in these 3 dimensions that we already specified for our class, and that's it. And this is also the only thing that is absolutely required for this method to contain, because otherwise it would not work in the context of our BaseTypeIO to create actual CTL container objects. Okay, so this is the meta info method, and then we can continue with our first actual data handling method, and this will be the read all method, in which we want to read data from a container, from a file into a container, which will be an STD vector. And that is basically the whole concept of how these file IO implementations work. They read data from a file into a contiguous part of memory, which is an STD vector in this case. And the same goes for writing. It needs to write data from a contiguous container into a particular file with respect to the properties that file should have. And yeah, so that's basically all we need to do. And then we just need to fix some things that Qt Creator does not get correct in the first place. So we need all these, let me type them manually. We need all these template dimensions here. And then we should probably be fine already. Let me check. We don't need this actually. Yeah. So Qt Creator is not really really good in creating the function signature properly for this kind of heavy template work that we need to do here. So in this situation, we actually need our file, of course, because we need to read data from it. And we start with just opening the file. And I will be using Qt file reading functionality here, but it's completely up to you to also do that with a standard library, for example. Just for sake of convenience, I will be using the functionality provided by Qt here. Then we could potentially do some kind of check if we actually can open the file. So we want to open it, and we have how is it called? Shouldn't it be QIO device? No, maybe I need to include some further header here. And in case we cannot open the file, we can, let's say, just address some warning for us. So could not open file or reading or something like that. Just that we inform the user that something went wrong here, and for this we also need to include the QDebug header. And again, it's absolutely fine to use the standard library for that, using standard out and whatever, and files from the standard file handling from the standard library. And yeah, in this situation, we also need to return something, and I want just to return some empty vector then, because yeah, when we cannot open the file for reading, it's the only thing we can do, just return an empty container because there's nothing to read for us. After we have checked that, we are now good to go to read in something from the file. And what we first do is we specify the container in which we want to read in our data. And here comes the interesting thing, since this read all method is also templated, as you've probably seen, which is supposed to read something into a container of type T. But in our case, we specified that our raw data IO is supposed to handle files of type raw type. So that means if you think about, you have a file and you know data in the file is in 16-bit unsigned format, then you can tell your raw data IO that actually the file type is 16-bit unsigned. And even if somebody requests the IO to read something into a vector of floats, then you know that your raw type is unsigned 16-bit. You read the data in that format, and then we will convert it into the target format. So first of all, we read data in the particular raw type format that actually is in our file. And we will call that raw values. And we need to specify how many of these exist. And this is pretty simple because this is just the product of our 3 dimensions. And then I will just extract some information here, which we will be using. So we want to have the number of bytes that we need to read, which is quite simple. It's just the number of elements in raw values times size of one individual element of the type that we have. And I also need, I do not really need that, but I want to memorize that in case I'm using the queued file handling here. I have the chance to read in data of a contiguous block and then get returned how many bytes I've actually read. So this is what I want to do. I want to know how many bytes I read, and I get that if I just say from my input file I want to read a particular amount of data, and I need to read that data into my vector. And this is a pointer to, this gives me a pointer to type raw type, and for the read function we need to pass in a pointer to a character pointer, and for that reason this is one of the very few places where you can actually use a reinterpret cast properly without invoking undefined behavior. And we will just cast that and let the read method just interpret that chunk of memory as a character pointer, and then we tell it to read that number of bytes that we just computed here. So we tell it to read in at the most this number of bytes, and if it cannot read that many, it will return a different number of bytes that it has actually read here. And this gives me the chance to just simply compare if I've really read the number of bytes that I expected to be in the file. And then I can close my file because I've read everything that I wanted to. And now I can do what I just mentioned. I can compare if my number of bytes that I expect in the file is equal to the bytes that I've read. And if that's not the case, I can issue a warning. Something like did not read the expected amount of data, something like that. Could be way more specific if we would like to, but for the sake of brevity, I would just leave it with that very simple message here. And the only thing that we now need to do is we need to convert our data that we read in raw type, which can be any type we pass to our raw data IO implementation. We need to convert that to our target file type. So actually we are supposed to return something of type std vector with template argument t, and that's why we now need to do the conversion from raw type to t. which is quite simple. So we just create our vector of type t, which I will call red because I'm going to return it. And this shall have exactly the same number of elements as our raw data vector. And then I can just use a standard algorithm to transform the data that I need. I will read the data from my raw values, go through the entire vector. I will put out the data into my vector that I just created. And then I need my transformation function here, which takes a value of raw type, because this is the input we are iterating over the raw value vector here. This is my value, and my conversion function just needs to return this statically casted to type t. And that's all we need to do. So we have basically just went over all the values in our vector that we have read in, and transform the values, or just converted them into our target type, put them in a vector, and this is the one that we can now return. And that should already be it to read in everything in that file into a contiguous block of memory with the correct output format. And this gives us quite some flexibility, because we can always specify the actual data type that we have in our file, and still let that put into a different target format than the one that is in the actual file. And we will see an example of when that can become relevant in a few minutes. So we can just continue with read chunk, which is pretty straightforward now, but I will place that below here and copy all that crazy template syntax stuff. And I should not have deleted read chunk. Get rid of this here. And this is basically the same as read all, with the exception that this is supposed to just read one chunk of data at the particular location, and one chunk in the sense of the CTL is always considered to be one block of the dimension 1 times dimension 2. So the first 2 dimensions form a 2-dimensional instance, so to say. We have dimension 3 times of these chunks with this dimension product here, and this read chunk method is just for convenience if some user, for example, just wants to read in one slice of an entire volume file. So it's no necessity to read in the entire block of memory, just reading in the slice that is of interest, or also an individual projection. These are the two examples where this method would be used internally for providing this convenience that not the entire object needs to be read. And we can more or less copy the entire thing here and just do a few manipulations. And the first thing that we need to do is we no longer read in these 3 dimensions here. So we only read in something of that dimension, because that's what I just said. This is considered to be one chunk within these files. Number of bytes will stay the same. And then we need to shift our input file to the correct position. So we have this number of chunks that we need to skip in advance before we can read in the chunk that is of interest at the moment. And for that purpose, what we would like to do is we use our input file, and then we what do? We skip dimension 1 times dimension 2. This is the number of elements in one chunk, and then we multiply that by the size of our raw type. So this is the number of bytes in one chunk, and we need to skip chunk number times of these chunks, because these are the ones that are previous, and we want to read in the chunk that is at that particular position. And after we've done that, we can continue with, like previously, with reading in everything from our vector here, from our file into our raw value vector, number of bytes. We computed that here by the size of this vector, can stay the same. And close the file, check if we've read the correct number of bytes, and so on. And everything else also stays the same. So this should hopefully be it entirely for read chunk. And that brings us to the final method that we need to provide, and this is writing data from a contiguous block of memory into a file of our desired file type. So same thing goes here. I will put that below. Probably for the sake of ordering, I will move my meta info implementation on top. And then we have the same template, whatever thing here. And put the template arguments of our class. Get rid of that. I have no clue why the creator is not able to manage this properly, but we can figure that out on our own. Okay, so writing has a little bit of a difference here because we have some degree of freedom how we want to handle this situation. There are basically two things we could do. We could, one option would be to write everything that is passed in here, no matter how big this object is. And the other option is we write exactly this number of elements that we specified for our raw data I/O. And for the implementation in this tutorial, I decided for this option that I write exactly this number of elements, because in my thinking, I specify an I/O that shall only be able to handle files that have this dimensionality and contain data of this type. So when I write a file, my expectation will always be that it has exactly these dimensions and it has exactly this type, no matter what is passed in here. Then we would have the chance to check if the data input here has the correct dimension and so on. I will leave all these kind of things out for the sake of brevity in the tutorial, but I think you know that there would now be the chance to check if there are enough elements or if there are more, and then we can issue a warning, and etc. etc. But for here now, we will just write this number of elements that is are specified by the dimensions, no matter what we get as an input to the write method. So we start very similar to before. Now I would just call it out file, because it will be create an output, put in the file name that is passed in, and then do the same check as we did here. If our out file cannot be opened for write only in this situation, we could not open the file for writing. And then we return false in that situation, because this method is supposed to return success or not of the writing operation. And then we can continue to compute the number of elements that we want to write. And this is just what I said. We would have the chance to decide for the number of elements in that data vector and write all of them. But in my situation, I want to write the product of dimension 1 and dimension 2 and dimension 3. So that it will satisfy my expectation later on that files written with this particular file implementation will always have this size, and there will be no difference in the size when I put in something else to the write method. Yeah, and then we need to convert our input data in this situation into the correct format, or to the correct data type. That means now we need to do type T converted to raw type. And this is also basically the same as we've done previously. Create a vector now of type raw type. This is then the raw values with the the same, no, not with that number of elements, but with number of elements. We've just computed that. And then we again use standard transform and iterate over our input container. And you probably see that already, and I'm aware of that this is not really safe, because I have no verification that data actually contains enough elements, and that my raw vector actually also has enough elements to now take the data that we will be providing by transform. But as said before, we could verify these things, but we will not do so here, just to save some time. And then our conversion is very similar to before, just that now we have something of type T, and we need to convert that to raw type. Man, what the heck? Like this. And then we have all the values that are required to be written in the file in the correct format now. And then the only thing we need to do is actually write the data. And for that, I will do something similar to before. I will compute the number of bytes I need to write, which is the number of elements times the size of one of these elements, which are of type raw type. And then we get the number of bytes that have been written by using our output file and ask it to write a certain number of bytes. Same thing here, we reinterpret to a const character pointer in this situation the memory in our raw data vector, and we write a number of bytes, hopefully, and this will return us the number of bytes that has actually been written. And then we can close the output file and return whether or not the number of bytes was the one that we expected. So we can return something like bytes written equals number of bytes, and then this will return true if we've written the same number that we've expected. Otherwise it will return false. We could issue some message for the user here if it was not the same, but I will also save time here and not do that at the moment. So that should hopefully be it. And something we can nicely see now due to our IDE here is that we have not used this meta info object that is passed into the write method, and that's of course because we have no chance in writing meta information. If you were to implement a file type that can handle meta information in like a text header, like we have it in the NRD format, then you would be supposed to extract everything that is passed in this meta info object and then convert it into the correct, let's say, entry in the meta information structure of your file type that you're implementing and just writing the correct value. So basically every kind of well-known data format has its header structure, and then you just need to figure out where you place the information that is passed in here in this meta info object and just write that in the correct position in the header of the file that you're writing. And since we have no chance to write meta information in a pure raw data file, we have no use for that object. We can just ignore it in this implementation. Yeah, there's no chance for us to actually put it anywhere. Okay, then that should really already be it for the entire implementation of our raw data I/O. And if we did not make any stupid mistakes, we should be able to use it in our implementation here. And now we know that we are not fine with just specifying its raw data I/O, but we need to provide details about the dimensions in the raw data. And this is something that you need to know. If you have pure raw data files, you need to know how the dimensions in the file are. Otherwise, there's no chance in reading the data in meaningfully, except for just reading it into one big chunk of memory. But that's not really used for some applications, because if you want to interpret it as projection data, for example, you need to know the dimensions of the projections. And in this situation, I know that the data that I will be reading has the dimensions of 670 times 60 times 290, hopefully, if I'm not mistaken. And I know that my files will be in unsigned short format. And if I'm specifying that, I can use that inside my BaseTypeIO, and I don't need to mess around with any of the CTL container classes. So the raw data IO class is independent of anything from the CTL except for the meta info keys. So there is no connection to the voxel volume class or the projection data class or whatever. The only thing that you need to deal with is contiguous memory from std vector, either for reading in or for writing data out. And the only connection to the CTL is at this position, where you need to make sure that you provide meta info in such a q-variant map with the correct keys for the remaining parts within the CTL to be able to know where to look for the correct meta information in that variant map. Okay, so when we pass that in, we have our projection file, which is now the binary format, no longer NRD. We read projections, we read volume data, slice, and check test writing and reading. So we can take a look if that works out already. Okay, we have done some mistake, it seems. Let me just check. We have, oops, yeah, that's the common. Let me find out if I can, okay, want to cast that into the type and probably can't. Good question, why? Because I forgot to put return here, actually. Okay, and if we take a look at our results, then we see something strange happened for the chunk2D view. Ignore that for a second. And also something strange happened for the volume viewer. But we can see that our projections look, yeah, I think exactly the same as we had it previously. And if we take a look at the output of our testings, we can see that saving, loading projections and single views is fine. There's no difference between the original and the saved and reloaded file, but we have a problem with the volume. And the reason for that is quite simple, because here comes the point where the inconvenience takes place. Previously, we had the information about the size of the objects in the meta information of our file. So that means when I pass in a volume file, the NRD header had the information about the dimensions of the volume. In my case now, I specified this in a hard-coded fashion. I needed to do that because there's no chance for me to get that information from anywhere, and that means I cannot use the same IO object to read projection files and to read volume files. Instead, I need to specify a dedicated IO object to read in volume files. And in my situation here, I will create an IO for volume files, and I know that my volume files will have dimension 200 voxels in each dimension. And I also know that they will not be in unsigned short format, but they are in floating point format. And then I will just use this IO instead of the IO that is used to read projection files. And I will also use that in my test case where we test writing this volume. And again, we will come in a second to what this means here. And just take a look if that solved our issue. And we can see that we are now properly reading in chunks. We're also properly reading in our volume file in raw data format. Projections, we saw that already. And we can also see that there's no difference anymore. So there is one very small thing that I wanted to mention here. So if we would have our volume stored in a different format here, let's say we would have stored that in unsigned short format, then this would have been possible also with the previous example in the NRD scenario, because when we read volume objects, we can specify what data type it has. And as long as our data container our file implementation is able to handle that type, it will read in the data properly. If you, for example, think about the den file IO, we can read in float, double, unsigned short, and integer, I think, and this will be handled properly. However, we don't have this option for projection data, because in the CTL, projection data is always assumed to contain floating point values. And if we have a file that has no floating point values in it, but let's say in this example, like here, we have unsigned short values, then there would be no option for us in our other file IOs that we have to read in the file directly into projection data. We could use the NRD file IO, just this part here, and then use the read all method that you've just seen. We implemented that, and the NRD file IO has the same method. We could use read all to read in the values in a contiguous block of memory in an STD vector, and then we need to figure out how to convert that and put it into into projection data. But with this approach here of having a raw data IO that can specify the type that I want to use, we can let the IO do the job for us. So we have written the code for that. It knows that the data is in unsigned short format. It will convert it internally into floating point values, and then we get a projection data file from a projection data object that we can work in the regular fashion like we're used to in the CTL, like adding some values to the projections, rescaling them, and so on. And the same also goes for writing stuff. If we want, for example, to write projections in a particular raw data format that is, like in this situation, unsigned short, and we would use the regular IO of the CTL with like the NRD file or the den file IO, then we would write something like io.write, pass in our projections, and then this will automatically always create files with floating point values in the file, because that's just the way how it is implemented in the CTL. And this is now different because we have the option to specify how the output files shall look like. And if I specify unsigned short for my raw data IO, the file that is written will be in unsigned short format. This, of course, can have the consequence that you have data loss if projection data is available in floating point position, like extinction values typically are, and you save them in unsigned short format. There will definitely be data loss, but at least it gives you the option. If you, for example, scale your projection data before writing them into something that is more or less suitable to be converted to unsigned short, this is a pretty good option to do so, because then you can just write a file with a correct target format without needing to convert it on your own, or to think about some file writing that has the correct target type. Okay, so then I just wanted to briefly take a look into what these things mean here. We've come across the observation that we need to pass in the full type of the IO known at compile time here. And the same also goes if you think about the entire IO object here. So this IO object has a very specific type. It's a base type IO that is using raw data IO with these specified dimensions here. So there would be no chance for me to create a method that takes something of any kind of IO. So I'm not able to do the same thing that we have in very many places throughout the CTL, that I'm just taking something like a base class reference and can put in any arbitrary IO that I want. The only option for that would be to make this function a templated method, a templated function, but there are situations where you might want to avoid this. And for that situation, we have the option to extract one particular aspect of the I/O from the entire BaseTypeIO object. And this is the thing that you can see here. If we take a look in this save load method, we take a unique pointer just to something of type abstract projection data I/O. And this is now the same pattern that you're probably familiar with. We have a pointer to the abstract base class, in that case any I/O that can write projection data, and we can just simply create such an projection data I/O instance when we have our full I/O and use the method make projection data I/O. This will, you can imagine something like that. It will extract the projection writing and reading aspect of your full I/O and create an object that is of this base type for you. And then you can pass around this object that is only able to write projection data, but this can be used in a very generic pattern throughout any aspect in your code where you might need something like that. And if I were to use this same method here with a different I/O, let's say with the NRD file I/O, would be perfectly fine, because I then just need to ask my NRD file I/O to generate this projection data I/O subpart of it, and then I can pass it in here, and I have written my generically usable function here without it being required to be a templated method that takes any kind of I/O, with all the drawbacks that this would bring with it, like being a little bit harder to debug and so on. And the same goes for the volume I/O, and in this situation you need to decide for the type of volume I/O that you need. So this method can only take volume I/Os that can write floating point values. And this is also basically the main reason why we needed to do that, because this writing of volume data is templated, and this makes life a little bit more difficult. But in case you have some situation where you know exactly what you need to do, you only need to read and write projections, for example, or projection matrices or volumes of a certain type, then this can be written generically using these abstract I/O subclasses that can only write and read a certain aspect, and you can very easily let them be generated automatically using these make methods. And if you recall, we did not implement anything of that kind. It's already provided. It's all within the BaseTypeIO, and as long as you provide a file I/O implementation like we've just written with the meta info method, read all, read chunk, and write, this also satisfies all demands to be able to be used in this context where you can extract sub I/O aspects from that full I/O class. Okay, so this is all I wanted to say about this data I/O, except for some mentioning of potential extensions. So this is a but it is a quite limited version of how you could in total implement such a raw data I/O. I briefly mentioned that there would be the possibility to leave out the third dimension. If you know that from ImageJ, you could just specify the first two dimensions, and the third dimension will be just extracted from the size of the file. It will just look how much data there is and decide how many of these chunks of dimension 1 times dimension 2 will be created. This is also possible for this implementation here. We could just do that as well, but I decided not to do it because it's a bit simpler like that, how we did it today. Then we could implement something also inspired by ImageJ, like skipping a certain number of bytes. If there would be a header and we just want to interpret a file that has a header as a pure raw data file, we could easily implement something like that, defining also a number of bytes to be skipped. It might be a little bit tricky when it comes to writing, because then you would be required to write a certain number of bytes with some nonsense in it, because we don't know the target header format, but we could do that. We could just write some random numbers or just zeros or whatever of the correct amount of bytes. And yeah, then there are some minor things that we could do, like introducing some shortcuts when the types are the same. If we take a quick look back into like not read projections, we go into let's say this I don't know, read all method here, we see that we will always have this conversion using std transform to transform the data, but this is kind of stupid if raw type actually is already the target type. So if I'm using projection data from the CTL, which is in float format, and then write that to float format, or if I read in data in float format and it shall be read into a voxel volume of type float, there's absolutely no necessity to do a transformation from float to float here. And there would be a possibility to do some shortcuts here, would require us a few lines of code, and we would save this transformation in these situations. And then we could add any number of consistency checks, which I already mentioned a few times, that we check for matching sizes if there's enough data or if there's not enough, and give some warnings and exception cases and so on. And then there would also be a possibility to get rid of that specification of the data type here in the end. So if we only want to do the same thing that the other file IOs provide, that I explained a few minutes ago, that I'm only able to read in projection data when the file actually has floating point values in it, then there would also be the possibility to do a similar thing here. This would save us the effort to do the transformations, but it will also take away from us the possibility to read in data in a different source format than it needs to be in the end in the CTL. And that's why I decided for the option that I fully specify my files that I will find, because only this definition is the entire specification of the files that I will be reading. They will have this dimension and they will contain these values. And if I know these four things, I can read in data. And maybe as a side note, you would not be able to do a combination of defaulted data type and leaving out of the third dimension, because you can either get the third dimension by knowing how many bytes one chunk requires, and you only know that when you know the type. If you don't know the type, but you know all three dimensions, you can figure out some information about the type, because you can divide like the size of the file by the number of elements that are in the file. Okay, and that's definitely not a complete list of potential extensions of this implementation, but it's the first things that came to my mind when I was thinking about how we could potentially make this a bit more extensive and yeah, having a bit more flexibility, but there are definitely more things that we could change in that implementation. But I think it's like it is, we can use it quite nicely to read in raw data files, also writing them, and no longer being required of having actually files in a particular data format, especially if we would do the extension of having this skip certain number of header bytes, then we would be more or less entirely free of reading in any data container without being in struggle of implementing a particular IO for that. But I hope that I also convinced you that implementing such an IO is not that difficult. You just need to implement these four functions, of which I guess meta information can be the most trickiest one when it comes to really complex data container classes, which have very difficult header structure, for example. But the remaining ones, and probably the same goes for write when it comes to really writing the meta information in your file. I mean, in the end, if you don't write the data, then you don't write a correct file of type, let's say NRD. If you don't write the voxel size, for example, this is information you've just ignored, but it would still work. It's not like the case where everything falls apart. It's just that when you don't extract everything from here and write it into your target format, you just miss information that is not present in the final output file. But all in all, I think it's quite straightforward to implement such a file IO for any kind of file type, as long as you're able to read the files and know how they are structured, where information is, where the actual data starts and ends, and then you can just put it into a vector or write it from a vector, and that's it. All that is required to be functional with the CTL. Okay, so that was a lot of talking. Are there any questions regarding this suggestions? I don't know. Something not clear. Mm-hmm. Yeah, yeah, exactly. Yeah. I just used it like this here to somehow indicate that I can use my object, so I can use my IO that I would normally think, so I would expect probably for this test function to get an entire IO object to read something. But yeah, if I were not to use this one here, I would be required to do like this entire crazy thing and use the static member of this particular type. Yeah, so e- exactly. Exactly, yeah. That's also something that you can consider if you know that there is some particular base type raw data file that you will always find. So the device that you're using, the scanner, will always provide the same dimension of data and always the same data type. You can just predefine something like using my raw data IO, and then you can just say this is always this type, and then you can just, let's say, have it like that, and then you could also have from your particular raw data IO use the static method, the static function to create this projection data IO. That's something you could do. And you can imagine having like a set of these for, I don't know, high resolution images, low resolution images, and so on. And then you don't no longer need to always specify these things. You just have your predefined types that have certain dimensionality and certain value type, and then you can just use it. Like, it almost looks as if that was an implementation that you've just written for that particular file type. Yeah, so this possibility also exists, but I will just revert that here because probably this is, yeah, we have it as a comment here now. I think this in this situation, it's a little bit more structured when it comes to how the code developed. Yeah, but that's definitely a correct remark. It's not really extracting the projection data IO of that particular object, but of the type of that object. Yeah. Okay. So if there are no further questions, it will be the same as always. I will upload the recording of this tutorial and place the code in the tutorial repository. Also put a link to download the data that I was using here. So these 4 files in NRD and in binary format. And then you can play around with that if you like, or even implement your own file IO in the ideal case, because I think this is something that is really heavily learning by doing. If you've done that once, then it feels like pretty natural to do it because it's always the same thing, reading and writing from and to standard vectors. Kind of self-explanatory after you've done that once. Okay, yeah, then thanks for your attention, and we can stop the tutorial here.